video, I've kind of been dead, like a little, but in this video, I just want to talk about something interesting. Well, not really interesting. Well, it is interesting, I guess. It's actually a good way as a first look into topology. What I want to talk about. Oh, that pen doesn't work. So today I want to talk about a little thing that I think is an interesting way to start topology, and I think it's an interesting way to get people into topology. It's the idea of a homeomorphism. Now, what I want to start talking about is that why would this be something to get people started off on topology, right? Well, I think anyone that's ever looked at any kind of like math memes or math meme pages on like Instagram or whatever, they've seen the meme that, oh yeah, topologists think that the fucking donut and the coffee mug are the same thing, and they're kind of right, because the thing called homomorphism, right? Some explanations like, oh yeah, they're Guinness one or whatever, right? But to actually understand why, we need to understand this concept of a homeomorphism, right? So the first thing I'm going to talk about, continuity. Second thing, what actually a homeomorphism is. And lastly, constructing a torus, right? Okay. So, we're going to go with continuity first. So, I think everyone has kind of learned like some, not really rigorous definition of continuity, and what goes something along the lines of this, right? If you can draw a function without raising your hand, whatever, it's continuous, right? Like, not continuous. Well, yeah, right, not continuous. That's true. But what if you want to generalize it? How do you say, how do you generalize this concept of continuity? Because you can't graph some functions on some spaces, right? So we introduce, we introduce a more rigorous definition of continuity. We say a function or mapping, is continuous. That if this is first of all, well, not really first of all, if for some open set, let's say V, in the subset of Y, of course this mapping, where F is of course mapping from, let's say, some spaces X, topological spaces X to Y, some V in Y, for some V in Y, and V is open, the pre-image of V is open in X, right? This is a much better definition in my opinion, right? It's definitely much easier to understand rather than pick a pen, generalizing it. It seemed a little bit weird at the beginning, but it's actually really cool and really useful. Now, I actually want to talk about the whole concept of this, which is a homeomorphism. A homeomorphism, we say some mapping. Yeah, a mapping. And let's say from two topological spaces again, X to Y, is a homeomorphism if three conditions are satisfied. 1. F is bijective, right? 2. F is continuous. And third of all, the preimage of F is continuous. Yeah, these are the three conditions for something to be a homeomorphism. I kind of want to explain. I gotta explain what a homeomorphism is. That's kind of just like, okay, what is this? A homeomorphism is just it preserves the topological properties of a space for the topological of a space from one space to another, right? There's a really good, I think, animation on Wikipedia of actually the thing we're talking about, which is a donut to a cup. Yeah, it's really nice, and it kind of helps you see what a homeomorphism is. Now, now I want you to think about a little bit more about it, right? So we have a homeomorphism from, say, a donut to a cup, right? This is a terrible drawing, but these are homeomorphic. We say there exists a homeomorphism between two spaces. They are homeomorphic, like a donut and a cup are homeomorphic. Now, now, I think another really, as I said, the animation makes it look much, it's much more intuitive than, oh yeah, that makes sense, I guess, It's much more intuitive way to think about it and learn about it. Now, I actually want to define what donut is, but now I'm actually use technically a torus, because I think this is also a good way to learn about a thing called the quotient topology and get into it. So, a torus, right? A donut. So, we say first we need to find a few things. We have to first find a thing called an equivalence relation. A relation really is an equivalence relation if, again, three conditions are satisfied. 1, x is equal to x. Right? That makes sense. 2, x is equal to y if and only if y is equal to x. And 3, if x is equal to y is equal to z, then x is equal to z. That makes sense, of course, if you think about it for a second, because, of course, x equals x. This makes sense. I don't think there's anything that's too counterintuitive here. It may just take a little moment of thinking at max, but I think everyone can handle it. Now, there's something I want to call an equivalence class. An equivalence class is just, we define an equivalence class. This thing is dying. We say this is an equivalence class. We define it to be the set of all y in x, for where x is in x, where I'm just gonna so that y is equivalent to x, or x is equivalent to y. because they're equivalent as we saw before. Oh god, this thing's actually dying. The poor marker. So yeah, that's what we call an equivalent class. Now we can create the set of all equivalent classes on X, which I'm just going to denote by we say this is the set of all equivalent classes on X for all X within X. It's the equivalent class of X for all X within X. Right? This is now this brings something important to us that we now want to think about. We want to define now the open set on this. Right? We want to find the open set on this. So we say some subset U is open in, open in if, of course, the union of all equivalence classes that are subsets of U, subsets of U, let's say the equivalence. Man. This is, of course, in and of itself, a subset of big X. Of course, this is a subset of X. Very clearly. Now, this to be open if, of course, this is just open in X. This little thing here, the union of all of these subsets of U are, of course, open in X. No, this is pretty clearly easy to see that this whole thing is a subset of X in general, because, of course, this is for X in X, and, U in itself is a subset of X, so it's not going to, it's not going to be, not a subset of X. So we just define it to be open if is open in X, right? And with that, you can pretty easily construct the quotient topology. Now, there's actually two ways to define it, but I'm actually going to review the other one in just a second, right after I actually define a torus or donut. A torus is defined by the relations x, y is equivalent to x1, y is equivalent to x, y plus 1. Right here. Right? The order pair of x and y is equivalent to the order pair of x plus 1 and y is equivalent to the order pair of x and y plus 1. This would be actually pretty easy to see why this would be a torus. Let me see if I can get a piece of paper out real quick. Alright, so let's say for this piece of paper here. Imagine this as a plane, except for, of course, a square instead, but I think this will do this just fine, I think, for now. So we say xy is equivalent to x plus 1. So we fold this over. And then we say is equivalent to x, x and y plus 1. So that'd be bringing this, like this, to the other side. And I think if you can imagine that, that would be a donut, right? Or just wrap it around. That would very clearly be a torus. I think you can see that, and I think it's a cool way to imagine actually the quotient topology. Otherwise, the next one we're going to describe might be a little harder to imagine and think intuitively about. So we say I think we use a thing called a quotient map. A surjective map is a quotient map if a surjective map is a quotient map if it satisfies a condition that we actually call strong continuity. The way we define this condition is that for if P, say this map P, that's terrible. P maps from X to Y, then we say that for all B that are subsets of Y, this V is open, and if and only if the preimage is open in X. Yep. You can see why this condition may be called strong continuity. It's actually a very interesting condition. Though I think you can be able to see that for this quotient map, between some given set, and like A, this map between some given set A and space X, and there only exists one topology with respect to P that well, there's only one topology with respect to P, and we call it the topology induced by P. That's gonna be the end for this. I'm sorry for making it kind of low quality, the terrible handwriting, my dysfunctional marker, but I hope you enjoyed it and subscribe for more. Hopefully that is, and I don't go on like a month-long hiatus like I did last time. My other topology lecture, and never be a second one. Again, I hope you enjoyed. Subscribe, please. I'm new. Have fun, yes. Learn topology. Go have fun. Actually, if you want to learn more, there are some good resources online. You can use Monkers. I think that's how you pronounce it. Topology, which is a good book on points at topology, and then there are some resources online specifically for the quotient topology and homeomorphisms. Hope you enjoyed it.